All right, we're going to look at a quick example that is dealing with a binomial distribution problem. We are going to go through and figure out its exact probability and then also use the normal curve to approximate the probability of the binomial example that we're working with. All right, but we're going to start off first off with just using the normal binomial distribution formulas and information. So for this problem, it's wanting us to compute p of x using the binomial probability formula. And just as a reminder, the binomial probability formula is this guy right here, that p of x equals n choose x, n c x, times p to the x times 1 minus p to the n minus x. All right, we're going to do that for n equals 51, p equals 0.07, and x equals 0.44. So there's going to be two ways to put this into your calculator. One is if we're using this formula right here, then we're going to have our n, which will be 51, choose our x, which is going to be 44, times our probability of 0.07 to the power of x, which is 44, times, and then 1 minus 0.07, 1 minus p, to the power of n minus x, so that'll be to the power of 51 minus 44. All right, so we type all this in. We're going to do 51 and then get to the NCR, or get to our combination. We're going to go into math and then go over to probability and then down to number 3. So we have 51 choose 44 times, and then we have 0.07, 0.7 to the power of 44 times, and then we can do the 1 minus 0.7. If you put 0.3 there instead of 1 minus 0.7, that'll be fine. To the power of, and I'm going to put parentheses here because I need to do 51 minus 44 in the exponent. So we're going to get 0.00387. And going to 4 decimal places, we're going to end up with 0.0039. Okay, now there's another way to do it in your calculator that might be a bit easier. We can go to the binomial distribution. So we are going to go to our distribution, so second vars. Then we're going to scroll down until we see our binomials. All right, we have the binomial probability distribution. So this will be us finding the probability of p of x. And then this is our binomial cumulative distribution function. So we're interested in A. So let me go back up and highlight that. And now I'll make a note here for us that whenever we do this, we're going to have binom PDF. And then we're going to list 3 things. We're going to list our n, our p, and our x. And it helps me to remember that those are in alphabetical order. So our n is 51. Our p is 0.7. And our x is 44. And sure enough, we're going to still get that 0.0039. Okay? So it's wanting us to now determine why we can use the normal distribution to approximate the probability. Well, the reason we can do that is because n times p times 1 minus p is greater than or equal to 10. So because it's saying that we can do it, this is what we're assuming, is that n times p times 1 minus p is going to be greater than or equal to 10. So that's going to be us going through and doing 51 times p, which will be that 0.7, times 1 minus p, or it'll be the same as 0.3, but 1 minus 0.7. So I'm going to come over to the calculator and double check. So we're going to have 51 times 0.7 times 0.3, and we're getting 10.71. So sure enough, we are greater than or equal to 10. So the normal distribution can be used to approximate the the probability for this binomial problem. Okay, so now we're going to actually go through and use the normal distribution to approximate that. So for our part right here, we're going to approximate it. So again, I want you guys to remember that we're coming through and we have something like this. So pretend that's a nice, pretty normal curve, please. And we need to find our mean. So we want to know what's right here in the center. And that's going to be our mean, or our mu sub x. So that's just going to be n times p. So our n is going to be 51 times p of 0.7. So 51 times 0.7 is going to give us 35.7. And then let's go ahead and find our standard deviation. And that's going to be the square root of the n, so 51 times p, so that's 0.7, times 1 minus 0.7. And I actually already did the n times p times 1 minus p, but I'm going to go ahead and work it out again from the beginning. So I'm going to go and get my square root of 51 times 0.7 times, I would need to do parentheses for 1 minus 0.7 and then close the parentheses twice because we're closing it for this set and for the entire square root. And that's going to give us approximately 3.2726. So we'll use that for our standard deviation. All right, so let's get an idea of what's going on here. So we have a mean of 35.7. And our probability is at 44, so that's going to be further to the right. Now the problem is that 44 is just this one line. And with our normal distribution, this is all continuous. So we have like 44, 44.01, 44.02, and so on and so forth, as well as all the little teeny tiny bits in between there, because it's continuous. So we can't find the probability of a line because there's no area to this, there's no thickness to it. So what we have to do is we have to go a little bit above and a little bit below so we can have a thickness to it. So we want to have a width of 1, so we're going to go a half above and a half below. Well, not a very good picture, but this will be 44.5, and the below part will be 43.5. So we're going to find the area in between those two. So we need to find z-scores. So the top z-score, we're going to take our data points, that 44.5, minus our mean of 35.7, over our standard deviation of 3.2726. And let's work that out in the calculator right quick. So we're going to do that 44.5 minus 35.7 divided by 3.2726. I will have a teeny tiny bit of rounding error because I rounded our standard deviation down there. And this is giving us about 2.69. And I'm only going out 2 places because this is a z-score. So the z-scores are only going out 2 places. All right, our next z-score, so for our lower number, is going to be 43.5 minus 35.7 over that standard deviation of 3.2726. And we'll go back and figure this out. I'm going to be a little bit lazy here on the calculator. I'm going to do second enter. I'm just going to pull up my last entry, and I'm going to change that from a 44 to a 43. And we're going to get 2.38. And again, I'm only going 2 places because this is a z-score. So 2.38. And now we're going to look this up. So we're going to look up the areas. So we'll look 2.69 up first. So we have 2.6, then we're going to go all the way to the end, 2.69. We have 0.9964. Okay, so that'll be our area. And now let's look up the area to the left of 2.38. So 2.38 is going to be right here, so 0.9913. And then we would just subtract. All right, we're going to get 0.0051 whenever we're using our table. Or if we go through and want to figure this out, using our calculator, we can do that as well. So we were trying to use our normal distribution to find the area between 43.5 and 44.5. So if you remember, or if you don't, I'll tell you real quick. We're going to go to our distribution, so second vars, and our normal CDF. That's our cumulative distribution. And so for the normal CDF, we're going to list four things. We're going to have our lower bound, our upper bound, our mean, and our standard deviation. All right, so we're going to go from 43.5 to 44.5. We have a mean of 35.7, and we have a standard deviation of 3.2726. And we're getting 0.00499, so that's going to round up to 0.0050. So using our technology, we got 0.0050. So you'll notice these are off by a 10,000th, meaning they don't match by a 10,000th. That's okay. With these answers, a lot of times there's an answer that they're after, but then there's an allowance of a 1,000th or a 10,000th above or below. So by how much do the exact and approximated probabilities differ? Well, the exact probability is the one we went through and used our binomial probability formula for. So the exact one is right here. So that's our exact, that 0.0039. And then our estimated one, I'm going to use this 0.0050. So the difference, I'm just going to subtract so that I'm ending up with a positive number. So we're going to have 0.0011 for our approximated, the difference between our exact and approximated probabilities.